The theory of plate tectonics unified the earth sciences as never before. All sorts of geological phenomena, from earthquakes and volcanoes, can be understood in the context of moving plates of the Earth's surface. In this lecture, I examine the underlying causes of these violent crustal events, and we're going to see that most earthquakes and volcanoes arise from dynamic processes associated with plate motions. In this lecture, after reviewing the evidence for plate tectonics, I'll examine the nature of the Earth's tectonic plates, and there are three different kinds of dynamic boundaries. These are, first, the divergent boundaries at which new crust is formed, the convergent boundaries where old crust is swallowed up, and finally transform boundaries where two plates scrape by each other. We're going to see that these boundaries control the locations of most of Earth's earthquakes and volcanoes. In the last lecture, I showed how the theory of plate tectonics brought a kind of unity to the earth science, and it brought together observations from all different sorts of disciplines of the earth sciences. We saw 6 lines of evidence for plate tectonics, the shape of the continents, North and South America, fitting so beautifully with Europe and Africa. We saw the matching rocks and fossils across the Atlantic Ocean, fossils from New England matching up exactly with fossils in Wales, diamonds in Brazil matching up with diamonds in South Africa. We saw that earthquakes and volcanoes had a very peculiar and distinctive distribution. They were in bands and chains, particularly the bands and chains of earthquakes and volcanoes called the Ring of Fire around the Pacific. And we'll see more in this lecture about why that Ring of Fire occurs. The discovery then of ocean floor topography, the mid-ocean ridges, that mid-ocean ridge of the Atlantic, which exactly parallels the coastlines of North and South America on the one hand, Europe and Africa on the other. Then the 5th line of evidence was the ages of volcanic rocks on islands in the Atlantic. The farther away from the mid-Atlantic ridge the island occurred, the older the volcanic rocks which formed it. And finally, the absolute smoking gun of plate tectonics, the magnetism of the ocean floor, the parallel stripes of magnetic rocks, which were not only parallel but also symmetrical about the ridges, so that some magnetic stripes were aligned according to the modern-day North Pole, but others had that curious property of being flipped 180 degrees, so that the magnetic north actually faced to our South Pole, a phenomenon that indicates the Earth's magnetic field has flipped many times in history, but also pointing to the mechanisms of plate tectonics. In science, simple theories that explain a wide variety of observations into a single unifying framework are the most valued. Plate tectonics is such a grand theory. It ties together data on minerals and fossils, on earthquakes and volcanoes, on surface geology, and also on the structure of the Earth's deepest interior, the mantle. Plate tectonics is crucial to understanding long-term variation of climate also, the distribution of ore deposits, and pathways of life's evolution, as we'll see later in this lecture. So in this lecture, we're going to examine plate tectonics and its consequences in more detail. First, let's take a closer look, though, at the distribution and the physical characteristics of the plates themselves. Recall that in an earlier lecture, I talked about the Earth's interior as a layered structure. And I looked at 3 chemically distinct layers. The innermost layer was the core of the Earth, primarily iron metal with some nickel. The inner core was solid, the outer core was molten. And this huge ball of metal represents the densest part of the Earth. Then surrounding that, most of the volume of the Earth is taken up by the Earth's mantle, a region of fairly simple composition. 4 elements, oxygen, magnesium, silicon, and iron dominate, and dense minerals form this mantle of the Earth. And then the outermost layer is the thin crust, composed primarily of lighter elements in more open, less dense crystal structures. But we can also describe rock layers in a different way. We can describe the layers of the Earth rocks in terms of their rigidity, their brittleness, in terms of their strength. And so here we need 2 new words. And I want to focus on these 2 words, the lithosphere and the asthenosphere, which are the 2 great layers associated with plate tectonics. Now, the lithosphere, this includes the crust And the very top part of the mantle, it's a relatively thin layer. It's about 50 to 100 kilometers thick. It's also relatively cold, less than 1,000 degrees centigrade. And at those temperatures, the rock is brittle. That is, if you take a hammer and hit it, it would shatter, it would break like a brittle piece of ceramic. So this strong rock layer is the lithosphere. It overlies, it rides on top of a softer layer, the soft, hot asthenosphere. This asthenosphere layer extends deep into the mantle. It's hotter, temperatures typically over 1,000 degrees, and that's hot enough to make the rock relatively soft and plastic, more like a taffy, if you will, than a brittle rock. So you could actually, if you had a piece of asthenosphere and you could hold it in your hands, you might be able to slowly bend it without having it break. So this kind of rock can flow under the right conditions. Now, tectonic plates are wide pieces of lithosphere. Remember, that's about 50 or 100 kilometers thick, but thousands of kilometers across. And the lithospheric plates are shunted about as they ride upon the asthenosphere, which is mobile and moving. In this scheme, now, continents have to be treated as separate objects. Continents are much lighter material. They're like the froth or the scum that floats on top of your soup pot. So they're sort of afterthoughts. The places where we live, the continents, are really, even in the scheme of plate tectonics and these thin lithospheric plates, not very important at all. They're just always going to float on the surface because they're such low density material. They're always on the surface. So continents, even though they're moved around from one place to another on lithospheric plates, they themselves are permanent parts of the Earth's surface. If you look at a map of the world's plates, you see about a dozen large, rigid plates distributed across the globe. Most of us in the United States and in Canada live on the North American plate. That extends from the Mid-Atlantic Ridge all the way to California, but not quite to the coast of the southern part of California. So people who live in Hawaii and people live in the California coast from Los Angeles and San Diego up to portions of the westernmost region around San Francisco, they live on the Pacific plate. And that Pacific plate is moving to the north relative to the North American plate. The continents of South America, of Europe, of Australia are all contained on single plates called the South American, the European, and the Australian plate. But Asia is split into at least two plates, and that depends on how you divide the boundary between North America and the Eurasian plates. Also, we have the African plate. All of Africa appears to be on one plate, but it also appears to be beginning to split apart now. So eventually, Africa may be split into two pieces. And that's a plate tectonic process which is ongoing, as we'll see. If you look carefully at a map of plate boundaries, you also can see the relative plate motion often indicated as arrows. And it indicates where two plates are diverging, that is, moving apart from each other, where they're converging, moving towards each other, or transform, where they're scraping past each other. And I want to look at these three different kinds of plate boundaries in much more detail now. Remember, we have three kinds: divergent, convergent, and transform. I want to look at the divergent boundaries first. Divergent boundaries always mark elongated zones along which new crust is formed as volcanic material. Now, two plates are going to diverge above a region where mantle convection brings heat to the surface. So if you can imagine convection going on in the mantle, huge convection cells that are going on in the mantle, and as material is brought upward and moved side to side, that's where divergent boundaries occur. You have excess heat coming up. That excess heat caused partial melting of the near-surface rocks. This supplies magma to these volcanoes as the plates move apart. The lava produced at ridges is typically a basalt. That's a dense black rock, rich in silicon and oxygen, magnesium and iron, just like the mantle. Basalt forms the foundation for all of the ocean crust in the Earth. And since the oceans are roughly 2/3 to 3/4 of the Earth's surface, that's one of the reasons why so much of the Earth's surface is covered by volcanic rocks. Indeed, I mentioned before, 80% of the Earth's surface, well, a lot of that is the oceans. Now, the Earth's surface displays many prominent divergent boundaries. Of course, the most famous, because of its discovery in the 1950s was the Mid-Atlantic Ridge. That extends for tens of thousands of kilometers, 60,000 kilometers, and it's now spreading at a rate of roughly 2 to 4 centimeters per year. That's about an inch per year. You can actually make satellite measurements, laser measurements that can detect that increasing distance. This is how it works. You have 2 points that are set in rock, one in North America, one in Europe. You have laser satellites that can measure distances to better than a fraction of an inch. And so therefore you can measure the distance between North America and Europe, and year by year that distance is getting longer. It isn't that airfares are going to go up anytime soon, but the distances are getting measurably larger. It's amazing that we have that technology now. By the way, the Mid-Atlantic Ridge passes right through the volcanic island of Iceland, and you can actually study the volcanism associated with the spreading right at the surface of the Earth at that point. I want to do a quick calculation, another one of these back-of-the-envelope calculations, because if you can imagine that the Mid-Atlantic Ridge is spreading at the rate of 2 to 4 centimeters, that's roughly an inch a year. So if the Mid-Atlantic Ridge is causing spreading at an inch a year, how long did it take for the Atlantic Ocean to open up? The Atlantic Ocean is roughly 3,000 miles across. You have 5,280 feet per mile, and then you have 12 inches per foot. So you just multiply 12 times 5,260 times 3,000. That gives you the number of inches, and at 1 inch per year, it turns out that's 190 million years. Well, it sounds like a long time, but in the context of Earth history, 190 million years is nothing. The Earth's 4.5 billion years old. The Atlantic Ocean has occurred in just a blink of a geological eye. The entire 3,000-mile wide Atlantic Ocean didn't exist 200 million years ago. So if you play the tape backwards at the current rate of spreading, you can imagine the Atlantic Ocean actually began to open up roughly 200 million years ago. That's when Europe and North America split apart. That's when Africa and South America began to split apart, began that spreading process which continues today. And it turns out this is only the very latest in a long history of openings and closing, opening and closing again of the Atlantic Ocean. This process has occurred on a cycle of roughly 500 million years or so for at least 3 cycles to our present knowledge. One of the most intensively studied divergent boundaries is the Juan de Fuca Ridge. That's a ridge that's just a few hundred kilometers off the coast of Oregon and Washington State. Now, the reason this ridge is so intensively studied is, well, there are a couple of good reasons. One of them is that there are great oceanography departments at both the University of Washington and the University of Oregon. And they're well equipped with ships. They can easily get out to these ridges. And rather than sailing halfway across the Atlantic, 1,500 miles to the middle of the Mid-Atlantic Ridge, you can just sail a nice, pleasant day's journey, a few hundred kilometers off the Washington and Oregon coast. You can have your ship there in no time, and it's very easy to study it. So this is one of the most accessible ridges of this kind available. This is the first place, by the way, that magnetic anomalies were discovered. So when people describe the spreading of the mid-ocean ridge and the magnetic anomalies on either side of the ridge, it was the Juan de Fuca Ridge where the very first data was collected. There also, because it's so close to a coastline, there's constant monitoring of the chemistry of the ridge, of the volcanic activity. There's seismometers that are down there. And if there happens to be a new volcanic eruption where a particularly strong volcanic event occurs, people can be on hand very, very quickly to the Juan de Fuca Ridge. So that's a very important site, and you'll undoubtedly see that described in the newspaper. There also is a very great deal of interest in the biology of the Juan de Fuca Ridge, because here's one of these places where you find fascinating deep-sea hot hydrothermal vent communities, and I'll tell you more about that in a little bit. Another important spreading center is the East Pacific Rise. That's a major divergent boundary in the South Pacific Ocean. There we have the highest spreading rates known, as high as 17 centimeters. That's about 7 inches per year have been measured at that East Pacific Rise. Another intriguing aspect of the East Pacific Rise is that the spreading is not exactly symmetrical. One side of that spreading center moves about twice as fast as the other side. And we don't fully understand that phenomenon, that dynamic yet, but it's one of those little interesting things that the Earth throws us every so often, another curveball. Another major divergent boundary is located in the Indian Ocean. However, this one is very poorly studied. We know almost nothing about the ridge in the Indian Ocean because it's a very remote locality, far from any big oceanographic facility, and also apparently the weather conditions in the Indian Ocean can be quite severe, and so it's a more dangerous and difficult sort of place to do oceanography. So you think about the vast amount of area on the ocean floor and the tens of thousands of miles of ridge systems, and we're only just beginning to understand and study these systems. All of these ocean ridge systems display complex hydrothermal systems. This is where seawater filters in through cracks and fissures on the ocean floor and then gets heated up by the volcanic activity, comes bubbling to the surface, sometimes in mineral-laden hot waters called black smokers. There are also rich biological communities at these black smokers. These are communities of organisms that thrive in the deep hot water, and apparently, astonishingly, these are communities that don't require sunlight to live. The old biological paradigm that all life gets its energy from the sun is now proven to be wrong. The black smoker communities get their energy from the Earth's inner heat. And they're based on microbes that actually eat rock because of all the chemical energy that's held in these rich mineral precipitates that are coming bubbling up through the volcanic system. Extraordinary discoveries. And keep watching the news for more on that, because every month we're learning more about these strange biological ecosystems deep in the ocean. Once again, the Juan de Fuca Ridge is the ridge that is most studied in this regard, but biological communities have also been found in the Atlantic on the Mid-Atlantic Ridge. They've been found in the East Pacific Rise, and they're undoubtedly going to be found in the Indian Ocean as well along that ridge system. Well, now, think about this process of a divergent boundary. If mantle upwelling occurs beneath a continent and a new divergent plate occurs, then the continent may actually start splitting apart. See, mantle upwelling doesn't care whether there's a plate or a continent or anything else. It's just going to go ahead. And if a plate brings a continent over one of these divergent areas, then you can have a continent actually starting to split apart. That's what's happening with the Great Rift Valley of Africa. There are also places in the American Southwest. There's places in New Mexico and Arizona where it appears that volcanism is occurring, and there may actually be a slight spreading, a slight rifting in areas in North America as well. Who knows whether these will ever develop into new oceans, but certainly the Earth is a dynamic place and all sorts of things may happen. Okay, let's turn our attention now to convergent boundaries, the second kind of plate boundary. These mark places where the motion of two plates is toward each other. It's a situation that arises above zones of downwelling mantle convection. Now you can imagine this situation. Divergent plates occur when mantle comes up and spreads apart, and then you have other places where mantle convection is like this. It's coming down. As that mantle convection goes down, the plates converge, and one of them plunges beneath the other one. Now, there are three kinds of boundaries that you can imagine in a convergent situation. You can have two oceanic plates, two chunks of ocean that come in contact. A second possibility is one of the plates can carry just oceanic, the other one can carry continental material. And the third kind is when both plates carry continents. Because continents cover only a small fraction of the Earth's surface, or about less than a third, the continent-continent type of collision is much, much less common. So indeed, something like 95% of all convergent boundaries have at least one oceanic plate involved. If neither plate carries a continent, then one of the oceanic plates plunges beneath the other one. You just have a situation where you have an oceanic plate approaching one, and the one oceanic plate plunges beneath the other one. If one of the two plates carries a continent and the other one doesn't, then invariably the oceanic plate plunges beneath the one carrying the continent. The continent is the lighter material, and it's the one that's going to stay on top. Now, according to the prevailing view, if you think about these situations, I'll get to the continent-continent collision in a second, but let me tell you about the oceanic subduction first. According to the prevailing view, that the cold plates are dense. And you may think of plate tectonics as being driven by the spreading centers where new material is formed and pushed to the side, but a lot of geologists now think that plate tectonics is driven by the fact that cold plates, as they subduct into the mantle, they're dense and they actually are pulled down by gravity. So instead of pushing the plates apart at divergent boundaries, Its possible dynamic is more pulling the plates apart with gravity playing a role, and of course the convection cell driving the process all along. It's interesting. Is this a push effect? Is it a pull effect? That's one of those kinds of details that geologists constantly debate and is an active area of forefront research. Rates of subduction, by the way, are at the same rate as divergence, so a few centimeters a year, maybe 1 inch, maybe 2 or 3 inches in some places. That's a typical rate of subduction. The axis along which one plate subducts includes most of the deepest trenches on the ocean floor, and you can imagine why this is true. Places like the Marianas Trench, that long trench which is so deep on the ocean floor it could hold Mount Everest with thousands of feet to spare, is a place where one plate plunges beneath another one, and as it does so it buckles the leading edge of the plate it's plunging underneath, brings it down, and so you get a deep ocean trench in that sort of plate. This process of subduction it's accompanied by numerous deep earthquakes. And the earthquakes get deeper and deeper as the descending plate plunges deeper and deeper within the earth. Recall I also told you that subduction zones can be associated with intense volcanism. As one plate plunges deeper and deeper, it gets hotter and hotter. It also carries with it, remember this is an oceanic plate, it carries with it lots of water in the rocks, in the materials that are being taken down. And those materials, when they get hot, tend to melt. And when they melt, they form magmas which then try to rise to the surface. And so you get a whole series of volcanoes 100 or 200 kilometers inland. And that chain of volcanoes, you see them many places around the world. You see them, for example, in South America. You see them in the Cascades in Washington and Oregon. You see them in in Japan. You see them in the Philippines. These volcanoes are all associated with subducting plates in which materials molten and brought up to the surface as the plate descends below 100 or 200 kilometers. When subduction leads to a chain of volcanoes, the result is called an island arc. And there are many examples of these arc-like arrangements of volcanic islands. For example, the Aleutian Islands off Alaska, Japan, the Philippines, and many of the islands of South Pacific are of this island arc type. And of course, as I've said, subduction also leads to continental volcanoes. The examples found along the East Pacific Rim, the Andean volcanoes of South America, and the Cascades of the Northwest Pacific area. This kind of subduction also leads to many of the world's most famous volcanoes. In Italy, Mount Vesuvius, that's the volcano that killed Pliny the Elder. It buried Pompeii. That's just one of the many volcanoes of this type. Economic geologists are really interested in this process of subduction because the reworking of the crust by subduction can also lead to the solution and the concentration of valuable ore metals. Many of the world's richest metal deposits, including many of those in the Rocky Mountains, are associated with ancient volcanoes that formed near convergent boundaries. So the huge gold mines, the silver mines, the copper mines are very commonly places that were once in volcanic regions above a subducting plate, where the subducting lavas came up and the waters associated with them dissolved the ores and then reconcentrated them. For this reason, plate tectonics provides economic geologists with a whole new strategy for finding valuable ore deposits. Now, I told you I was going to come back to the idea of two converging continental plates, and this is a fascinating phenomenon when it happens. It doesn't happen often, but when it does, it's spectacular. Very occasionally, when two plates are converging, they carry continents, then the continental material cannot be subducted. The continental material is just too light to be carried down into the mantle, and so it has no place to go. And as the two plates come together, the two continents collide with each other and start hitting each other, colliding, crumpling up, becoming ever more contorted, ever more piled on top of each other until you form a huge mountain range. The tallest mountain ranges in Earth's history have been the result of colliding plates. The collision, the convergence of two plates, each of which carried a continent. Today, that's occurring where the Indian plate is colliding with China. And the Himalayan mountains, the tallest mountains in the world, are the result of piling layer upon layer of continental material into each other. That's why you find fossils at the top of Mount Everest, because these are layers of rocks that have been folded and contorted and pushed together and raised up. A similar collision 400 million years ago between North America and Europe caused the Appalachian mountain ranges. And when the Appalachians were formed in that period 400 to 500 million years ago, the Appalachians were once again the tallest mountains on Earth. They looked very much like the Himalayas, we think. Now, after hundreds of millions of years, they have rounded and eroded to the point where there's sort of more gentle hills now. There's some fairly big mountains in the Appalachians, but nothing like they used to be, nothing like the 30,000-foot peaks that may have once occurred on the Earth's surface as a result of this great collision between Europe and North America so many hundreds of millions of years ago. Okay, at last we come to transform boundaries, the third kind of plate boundary. These are basically faults where two plates slide by each other. Such boundaries are inevitable whenever you have a sphere that's broken into divergent and convergent boundaries. And as I said, the most common one is the San Andreas Fault. It's the longest highly active transform boundary on the surface of the Earth. Major earthquakes occur along this fault every few decades. Geologists predict that another severe quake must occur in Southern California sometime in the next quarter century or so. The stress is just building up too much. You also have transform boundaries along the ridge ocean systems. The ocean systems, if you look at a map of the seafloor, you'll see that the ridges are offset from time to time. And those offsets are also transform boundaries of a shorter sort. But they involve areas where plates meet. They're moving by each other, but they're not diverging or converging. So I urge you to look closely at a map of the ocean floor sometime and look for those tiny but very significant transform boundaries that just cover the area of the mid-ocean ridges. Geologists have also identified several quiet transform boundaries, ones that aren't moving. Plates meet each other, they're in contact, but at least for the time being, they're not moving very much. There's such a passive boundary, for example, between the Eurasian plate and the African plate. At some time in the future, these boundaries may move, there may be giant earthquakes along them, but at least for now, they seem to be quiet. It's large-scale mantle convection that drives plate tectonics, and it controls most of the Earth's volcanoes. I want to review this fact. You have volcanoes at divergent boundaries where new crust is being formed, and so you have a ridge of volcanoes. You have volcanoes along convergent boundaries that are roughly 100 to 200 kilometers inland from the actual boundary. But there's some other very well-known volcanic areas, including Hawaii and Yellowstone, that are smack in the middle of plates. So what's going on with these volcanoes? These areas are called hotspots. They're found all over the globe. There are about 100 of them around the globe. And they represent a different kind of mantle convection, which is as yet rather poorly understood. Hotspots seem to arise when a narrow plume of magma rises from deep within the mantle. Perhaps the core mantle boundary is the origin of these hotspots. That would be 3,000 kilometers down. The location of hotspots seems to be absolutely independent of plate tectonic motions. For example, if you look at the Hawaii chain of mountains, you see that that chain of mountains seems to have moved off to the northwest. The reason is because the plate itself is moving and the hotspot is remaining fixed. So you have a fixed hotspot. As the plate moves, progressively, the new islands, the new volcanic islands that are formed, appear to be more and more and more to the southeast in that chain of islands. What this means is, as you look at the volcanic islands, the present-day big island of Hawaii, where active volcanism is occurring, is the largest. It's the one where all the action is taking place. As you go farther and farther away from Hawaii, you see more and more eroded islands. And then if you do sonar studies even farther out, there's a huge string of undersea volcanic islands that is things that were once islands but are now eroded to below ocean level. It extends for hundreds of kilometers off to the northwest. This indicates that the hot spot has been fixed for a long time and the Pacific plate has been moving over it. There's an awful lot left to be explained about hotspots, and suffice it to say that their origin remains a very hot topic of research. Well, to summarize this lecture, we focused on three types of plate boundaries, each of which is a dynamic region of geological change at the surface. We have divergent boundaries, and that features ongoing volcanism and the formation of new crust, for example, at the Mid-Atlantic Ridge. We have convergent boundaries, which are sites where old crust is swallowed up. Earthquakes and volcanoes follow the path of the subducting plate. And finally, transform boundaries, where two plates scrape by each other at the sites of some of our planet's most violent earthquakes. In the next lecture, I'm going to tell you about the Earth's great cycle, the water cycle.